Hey guys, welcome back. We're getting into the complex ion formation now. It's a little bit modified from the original slides that I had because we've changed how we're handling this in the department. So things are a little bit easier for you to handle now. So I'm gonna go ahead and share my screen so that we can talk about these slides. Now, it turns out that metal ions can act as Lewis acids. So a Lewis base, remember, is defined as something that has a lone pair of electrons that it can donate to anything that has an empty space. And metal ions always have empty space. Okay, so they can act as electron pair acceptors. And they form complex ions with Lewis bases in the solvent. The formation of those complex ions increases the solubility of those salts. Okay, so if we have like silver, and we need to get more silver in solution than we could do through some salt that we had. We are able to add ammonia to that. That pulls that silver into solution, okay? And so since the silver is going into this thing, then it comes out like if it came from AgCl, right? And technically it does. That's an Ag plus a Cl minus. But if we're taking this Ag plus and reacting it here, that means that concentration is going down. And if that concentration goes down, more and more of this solid can dissolve because that Ag plus keeps disappearing. So that concentration of Cl can keep going up. Okay, so that gives us a way to drive that into solution. And that's what the effect of these things is. Now we call these complex ions. So we have formation constants for them. These are called KFs. You'll see that this says KF. That's what that refers to. Okay. What we need to know about this is that it changes the solubility. So let's see what that looks like. So if we're looking here, we have a solution that has AgCl in it, right? This is what we were just talking about. So AgCl, we get both of those ions in it. We take NH3 and we add that to it, and we get Ag and H32 plus. So now we have the formation of this complex ion, and that means the Ag plus has come out of the solution on its own and gone into this other thing, so that concentration has gone down, which means that we can then add more of that Ag to this. So this reaction, the one that we show down here, okay, that makes that far more soluble. And so while we used to talk about just the solubility of the AgCl, which has a KSP, right? And that KSP is equal to Ag plus times Cl minus. In the presence of the NH3, the solubility greatly increases because that Ag plus takes it out of there, right? So if we look at what that Kf is actually, what it looks like, we take, and our product is that AgNH3 2 plus. And of course, that's made from the NH3, which is squared, plus the Ag plus, which came from the AgCl. Okay. And those aren't added, those are multiplied. So that's the formation constant for this thing. And of course, that leaves that Cl minus there. So that's what that Kf looks like. Okay. So that's how we can work with this. All right. Now, that's really awesome. Okay? And we're able to do things that we weren't able to do previously. So that helps us. Complex ion equilibria gives us a way to talk about this. So we can calculate the molar solubility of AgCl using the KSP being equal to 1.6 times 10 to the minus 10th. And we know that when we do that, that KSP is equal to the Ag plus times the Cl minus. And I know that if I have an ice table for this, we'd have AgCl solid going to Ag plus Cl minus, which you cannot see at all because I'm writing over stuff that's already there, plus Cl minus. Start making it look weird. And of course, we don't care about the solid, so that isn't going to matter. Both of those start as 0, we're going to end up with a plus x and a plus x there. And so that's how we get the x squared is equal to the 1.26 times 10 to the minus fifth. And so when we solve for x, that gives me 1. Sorry, it's 10 to the minus 10th for the KSP. So when I solve that, i.e. I take the square root, then I get 1.26 times 10 to the minus fifth. Okay. So that's where we get that. That's great. But when we take and make this complex ion, this formation, we have a K for that. That's for the reaction Ag plus 2NH3 goes to Ag NH3 2, and that should be a plus. Where am I looking at? Oh, that should be a plus. And that gives me Ag NH3 2 plus over Ag plus times NH3 squared, and that has a value of 1.7 times 10 to the minus fifth. Okay, now that's taken from one of the tables in your textbook. Okay, you would have to be given those values. They're not present in the exam handouts, so you'd have to be given them if you were expected to work with them. Now the overall equation for this thing is then AgCl solid plus 2NH3 goes to Cl minus plus AgNH3 2 plus. That has a K value of AgNH3 2 plus times the Cl minus divided by the NH3 2, which can be gotten from multiplying the KSP times the KF. Okay, and so multiplying those two values together will give us the value that we're looking for, which is 2.4 times 10 to the minus third. So 2.4 times 10 to the minus third, comparative to that 1.26 times 10 to the minus 10th. And that's awesome because that allows us to see how much more soluble those things are. Now, I can go through and actually do the math and figure out how much more soluble this is going to be based on that math. We do not expect you to do that, okay? This is how it's done, but we do not expect you to do that. I do expect that you will understand how these two, how the KSP and the KF can become this K for the overall process. And so how would you calculate that K for the overall process? You may be asked to calculate that K. You may also be asked, what is the effect of the complex ion formation? And the effect is that that solid, AgCl solid, is more soluble than it was before. So that's what I'm expecting. Okay, so hopefully that is clear. Awesome. So, does the solubility of mercury 2 change in the presence of an excess of chloride? Well, I can see they've told me that I have a KF for this HgCl4 2 minus, and that implies that there is a solubility that comes from having enough chlorine around to get AgCl4 2 minus. We also know that there's a KSP for HgS, so Hg2 plus S2 minus, that's mercury sulfide, and that has a value as well. So this value right here is 1.7 times 10 to the 16th. This value is 4.0 times 10 to the negative 54th. It's really tiny. And so if we wanted to find a K for the overall reaction of HgS plus some chloride, going to become HgCl4 2 minus plus S2 minus. We need to make sure that we're balanced. I have one Hg, one S, one S, so I need to have 4 of those there. So that's my overall process. That K, which is equal to the HgCl4 2 minus times the S2 minus over the HgS, which is a solid, so that doesn't appear. Sorry. Trying to erase the mess that I made, and I shouldn't have put it there in the first place. Over the Cl minus concentration to the 4th. Okay, so that's the overall K, and that's going to be equal to the KF. That is actually an F. It's a little f, but it's an F, times KSP. And that's equal to 1.7 times 10 to the minus 16th times 4.0 times 10 to the minus 54th. Okay, So that value would be the K that we're looking for the overall thing. And it does increase the solubility. So the solubility of the mercury 2 chloride goes up. And that's because we've driven that reaction forward. Okay. So that is no different than what we talked about previously. Now let me actually calculate this value. 1.7 times 10 to the minus 16th times 4.0 times 10 to the negative 54. Oops. That's not a negative 16. That's a positive 16. 16. That looks better. And that gives me, and it's not going to fit there, so I'm going to put it over here, 6.8 times 10 to the negative 38. So it is more soluble. It's not great still, but it's more soluble than it was. And that's what we're talking about. That's what happens when we have these complex ions that form. So you need to be aware that the formation does happen, that we have a greater solubility because of it, that it drives that reaction forward. Those are the things I want you to know about that. Okay? This is another question, same kind of idea. Does the solubility of the cobalt sulfide change? Yes, it does. It's more soluble. Yes, more soluble. And what would the K be for that process? We'd take KSP times that KF, and that means 4.0 times 10 to the minus 21st times 5.0 times 10 to the 31st, because it says what is the overall K. And that overall K is then going to be 4.0 times 10 to the negative 21st times 5.0 times 10 to the 31st. And that gives me 2.0 times 10 to the 11th. Okay, so that's how that K value changes. Okay, and of course, the fact that we are now looking at a positive thing is far more soluble. We are able to get much more of that solid in solution. Okay, so that's what we're looking for there. Questions, comments, problems? I hope not. But if you have any, please let me know. I'm going to go ahead and stop here. I'm going to have to take a break from recording, and I will be back with you after my own class.